So if we look at this through the lens of product principle, to build a function from 0, 1, 2 to 0, 1, we have to do three things. We have to decide on f of 0, we have to decide on f of 1, and we have to decide on f of 2. So it's a three-step process. And at each step, there are two choices. And so by the product principle, 2 times 2 times 2 gives us 8. Y'all buy that? Okay, so there are 6 non-constant functions. So a constant function is something where everything maps to the same. Let's try this now in general. Let x and y. So let f and y, let x and y be finite sets. How many functions are there from x to y? And then how many non-constant functions are there? That's called generalizing. It's a conjecture based on what we've seen previously and guessing, okay, this number was this number was this. If we map them back together, maybe that's the formula. Notice how it worked a lot better to look at that as 2 times 2 times 2 than 8. If we had just had 8 as the answer, it wouldn't have helped us to generalize. I'm wondering if we can, your conjecture is excellent. I'm wondering if we can walk through the reasoning here to build our argument in a way that will. So can you take this and use it instead of 0, 1, 2 to 0, 1, make it be from an arbitrary finite set x to an arbitrary finite set y. Okay, here I have a proof that the number of functions from 0, 1, 2 to 0, 1 is 8. And now we have a conjecture that the number in general is the cardinality of y raised to the power of cardinality of x. And I'm saying maybe we could take this proof for the small case and make it be in this, we could repeat this argument, but instead of starting with 0, 1, 2 to 0, 1, we would instead, so where it currently says 0, 1, 2 to 0, 1, we could replace that with x to y. And the only thing we know about x and y is that they're finite sets. And what would you change about what I've written here? How could you use this as a skeleton for a proof that goes from any finite set x to any finite set y? Cool, y'all did a lot of thinking for an 8 a.m. class just now. I want to know that you know I really appreciate it. This will pop up as an exercise on an upcoming homework, so your thinking has not been wasted. What we just did was what I call the Polio Principle. It's named after George Polya, who was a fantastic mathematician who wrote a book called How to Solve It, which is like the Bible of mathematical problem solving, or whatever you consider a sacred text of mathematical problem solving. And it says, if there is a problem you do not know how to solve, find a simpler related problem that you do know how to solve. And this has become kind of famous among WCU undergraduates who go into PhD math programs. They say that this is incredibly helpful. In fact, they came up with a verb called polyaizing it. They take the problem, they replace it with a simpler problem. So here, the Polya version of the problem was to find all functions from 0, 1, 2 to 0, 1. And the larger version, to find all functions from x to y, where x and y are finite sets. And I kind of polyaized it for you. I started you out with this, and you went to this one. But what you'll have to do is go the opposite way. You'll have to start with a hard problem that you don't know the answer to, and then find, where is the hook I can start stepping up with? There's probably a mountain climbing analogy, but it's too early in the morning for me to think of it. But it's incredibly helpful. What I noticed is what no one did is no one tried to divide and conquer by brute force. So there are only 8 of these things, and you had groups of like 4 people. So what if you broke it up and you said, can you find all the functions where f of 0 is 0, and I'll try to find all the functions where f of 0 is 1. So what some of you did was divide and conquer by brute force, or brute force without divide and conquer. These are amazing things. Not because I think they're amazing, but because they're amazing.